radiation, typically 912 primary driver, and that's what the magnetic spectrum. I do want to point out a post-mission gate. Hopefully.
Okay, I did not hear a question in there. All right. Is that okay? Thank you.
Yeah, thank you. If you have additional questions, please in a discussion session later. So the next talk is Kosuke Namekata from Kyoto University about the coronal mass ejection on young suns, insights from solar and stellar observations and models. And 10 minutes plus 3 minutes.
Hello, my name is Kosuke Namekata from Kyoto University, Japan. So today I would like to talk about the observational signature of the coronal mass ejection from young sunrise stars, which was obtained as a result of the recent 5-year dedicated observation of stars in comparison with solar observation and model. So let me start from general introduction. So as you know, solar flares are sometimes associated with the coronal mass ejection, and in this movie. So these are also associated with the cool material eruption called the filament eruption and prominence eruption, which is the core of the coronal mass ejection. So these phenomena are basically explained by the magnetic reconnection model in the case of the sun. And sometimes this kind of CME damage the planetary environment, and so that's why it's very important for human civilization. So the focus of this talk is the young sun-like star, which provide a unique window into the young sun environment. So young sun-like star, I mean, here G dwarf is very important as the host of the young exoplanet where the formation of atmosphere is in progress. And also it's important as a proxy of the young our sun. So it is known that young sunrise stars are very, very flare active compared to the matured modern sun, and often produced the very large flare called super flares, whose energy is more than 10 times larger than the largest solar flares. And so that's why it is recently produced that these huge, possibly the huge CME and high energy particle associated can play the significant role in the planet atmosphere and stellar evolution. For example, in the form of the chemical changes and atmospheric erosion and aurora. So that's why the observing young sun-like stars should be very helpful for the understanding of the environment of the young sun. However, no observation so far has been obtained for the stellar CME from the young sun-like star before. So in order to characterize the stellar CME signature from the young sun-like star, we studied the new young sun-like star project. So our project method is like a long-term HR4 and sometimes multi-wavelength spectroscopic observation of the young sun-like stars. So in the case of the sun, solar filament eruption and prominence eruption, which, as I said, the core of the coronal mass ejection, often are observed as a signature of the blue-shifted HR4 emission and absorption. So this kind of the HR4 time result observation, we'll be able to find a Doppler shift in HR4 from the stellar filament eruption and prominence eruption. So our goal is basically to detect this eruption as an indirect evidence of the coronal mass ejection, and to estimate their properties like frequency of the masses and so on, and to reveal its overall picture with a multi-wavelength observation. So our major telescope is this Japanese 4-meter class telescope called the Seimei. So it is a relatively new telescope, and its great advantage is that we can obtain plenty of the observational time, like more than 30 nights per year for a given star. So it's a very strong advantage. Yeah. So this is an observation summary. So we performed multi-wavelengths, especially HR for monitoring observation of young sunrise stars for 5 years by using these telescopes. So our target star are basically two stars, Ikedor and V8 and 9 Hagris. So these are very good stars that produce super Fourier very frequently, and it is observable from the northern hemisphere, and it's very young. So we observe these stars basically using the Japanese 4-meter cross telescope for the HR for observation with a high signal to noise ratio observation and high time cadence observation with a large long-term baseline. And not always, but sometimes we have simultaneous test optical photometry observation, and we sometimes have a simultaneous observation with nicer soft X-ray observation, and sometimes we have a Zeeman Doppler imaging observation with TVL Navarre in France. So as a result of the 5-year dedicated observation, we obtained 11 HR4 super Fourier, and I will introduce a couple of interesting events in this talk. So this is already introduced in the several presentation, but this is the first discovery of the large filament eruption from the young sunrise star. So the left panel here is the right curve of the HR4, and as you can see, there is a significant super Fourier has been confirmed by HR4, and that's quite right. So we estimate that Fourier energy as 10 to the 33, which is 10 times larger than the largest solar Fouriers. So if you look at the HR4 spectra, so it shows clear blue shifted absorption component here. So this means that there is moving material in front of the star, and it is absorbing the stellar light. So we also obtained the temporal evolution with this blue shifted component. So here, time and wavelength spring, and I'm now plotting the spectra, HR4 spectra. So as you can see, we obtained the velocity change, and the velocity change was very similar to the surface escape velocity, surface gravity of the star. So based on this observational fact, we concluded that we detected the clear evidence of the stellar filament eruption on young sunrise star, as in this right panel, right imaginary picture. So actually, this is the stellar observation. So this is a point source observation. So we don't have any spatial information, and as in this imaginary picture, actually, but we have an answer in the solar observation. So we can spatially resolve the solar eruptive event. So we think that if we compare the solar observation and solar observation, we will be able to answer about the spatial information. So then we performed the sun other star analysis of the HR4 line for the solar eruptive event and compared with the stellar event. So the left here is the result of the sun other star analysis of the HR4 spectra, and the right is the comparison of the stellar event. So as you can see, the spectral variation of the sun other star eruption greatly resemble those in the sunrise star Ikedora. So we obtained the post-Fourier HR4 dimming, and we obtained the blue shaded velocity change with gravity. Although it is true that there is a significant difference in the time scale and velocity. So the spatial scale and energy scale is completely different. But this similarity suggests that the stellar filament eruption is just a large scale counterpart of the solar small scale filament eruption. So by continuing this kind of the dedicated observation, we discovered another event. So like a large prominence eruption. So in this event, so HR4 spectra show, as in the left panel, so the HR4 spectra show the blue shaded emission component. So previous one is absorption, but this is the emission component. So this is very simple. So by solar analogy. So this is just an off-rim prominence eruption. So there is no background, right? So this is an emission. But in the first event, there is this is on this event. So that's why this is observed as an absorption. So we found that in sunrise stars, like the sun, we can distinguish the off-rim event and on-disk event only from the HR4 spectra. So this is a very strong advantage of the HR4 observation, and also it's a very good advantage of the G dwarf observation. So it will be a bit difficult in the M dwarf observation. So this is already introduced by Kai Hector, but we performed one-dimensional MHD simulation, and the simulation well observed the observed spectra. And this simulation suggests that this prominence eruption could eventually become the coronal mass ejection, as in this in the Kai's talk. So please remember this his talk again. So unfortunately, we have a simultaneous X-ray monitoring observation by NICER, and that simultaneous NICER X-ray observation show that possible X-ray coronal dimming associated with the prominent large prominence eruption event. So as already introduced by Rachel, so this coronal dimming is a kind of the different CME signature in the case of the sun. So we can observe, we will be able to find some signature in the sun, like here. So this is caused by the evacuation of the coronal material associated with coronal mass ejection, and this is actually observed 2 hours after the large prominence eruption on Ikedora. So this will be the first multi-wavelength characterization of the stellar CME signature. So we found several some signature of the different material. Okay. So prominence mass was actually much larger than the evacuated coronal mass by 1 order or 2 order of magnitude. So I don't know whether this is reasonable compared to the solar observation, but in the future, solar observation comparison with the solar observation is needed. So, and we also obtained the simultaneous spot mapping and magnetic field mapping simultaneously with prominence eruption and dimming event by using the Zeeman Doppler imaging and the test right curve inversion method. So this is the result of the mapping. So we found 2 large star spots when the prominence eruption occur on the limb, and we found there is a priority inversion line here around the large star spots. So in the case of the sun, the large priority inversion line could be one of the source of the large prominence eruption. So the scenario that the prominence eruption and dimming event occur around this mid-latitude large star spot with priority inversion line is very consistent with the solar observation. So this is the kind of the summary of the obtained picture of this extreme event on the young sun for that one single event. So we found large star spot around the rim, and there is a large priority inversion line here. And we also obtained the test white light flare. So the foot point is visible from the Earth. And we also obtained the large prominence eruption associated with the coronal dimming. So I think this data set provides the best example of stellar eruption to be compared with 3-dimensional numerical modeling, which was already introduced by Alini and Hurian. So finally, I would like to introduce the statistical result of the 5-year campaign observation of the young sunrise star. So the 11 superflare, among 11 superflare, 2 superflares show blue shifted absorption, and 2 events show the blue shifted emission profile. So this means that association rate of the CME signature against superflare is like 40%. It is relatively high than we expect. And we already know the flare frequency for this star. So by combining the flare frequency and CME association rate against superflare, we estimated the super CME frequency as 1 event per 5 days. It's very frequent. So please note that this is just a raw limit because we can characterize only the Rhino side velocity component. So probably we cannot detect the perpendicularly erupted prominence. So probably the eruption some frequency could be much higher than this. And interestingly, so we found that Ikedora's frequency is like a 4 CME signature per 8 superflare, but other star B8 and Hercules did not show any signature of CME among 3 superflares. So this may be a kind of the difference among different stars, but we are now rocking the events. So further investigation is required. So this is a summary slide. So the occurrence of the super CME on young sunrise star are inferred from the combination of our dedicated stellar observation and comparison with solar observation and models. So we found that they are very frequent, and massive. Actually, we didn't show the masses, but it was very massive compared to the largest solar CMEs. So in the future, we are now extending this kind of the multi-wavelength campaign to the radio observation and the far UV observation. So a new data is coming. So in the next Kurusa meeting, I would like to show you the new result. So thank you very much.
Say that 40% that you think is high. but
Yeah.
you would actually say that it's actually low.
Yes. Mm, mm, right, right.
Okay, I just done an estimate of what is their capital rate.
Oh, okay. Okay, so Freyan's question is, what is the mass loss rate of the from this kind of the CME event? So actually, in our paper, we didn't estimate of the mass loss rate in our group, but other paper like Martin Ratinger's paper team and other team estimate the mass loss rate, possible mass loss rate based on the observation. And I forgot the exact number, but there is an estimate. So in our upcoming paper, we would like to estimate the mass loss rate based on our observation. Yeah, thanks.
I think very quickly.
Do you have an explanation for why there was a delay when you saw the H alpha version?
Oh, so actually, I don't have any significant explanation, but probably actually the observation was very sparse, so time cadence is not good. So that is one difficulty. But I feel that in the initial phase, there could be some contamination with the X-ray flare component. So that's why that X-ray flaring emission can fail the dimming signature. So that is one possible explanation. Yeah.
Okay, for the remaining question, please. Okay. The final talk in this session,
It's fine.